Hello, everyone. Welcome back to ELEC3204. This is a revision session. So as I mentioned in my email that this revision session will focus on past papers because I will go through some equations. It will be difficult to record the live session when I write equations on board. I tried before and it doesn't record very well. So I'm recording this at home on my computer. So it's probably going to be a little bit slower than live sessions because I don't really have a board to write. I have to use my mouse. But I promise it's the same extent as your live section, live lecture on Friday. So that's the first thing to say. Second thing is that, okay, so you can see this is your course website. And if you go to the past papers, there are 5 past papers that are available to you. So this year, I encourage you to do revision based on those questions. So there are a lot of contents in the slides, and all the answers are based on the slides, actually. But exams and courseworks that are designed to be a little bit challenging, which means there will be a little bit of gap between the content in the slides and the answer to the questions. So hopefully, by going through these 5 past papers, I'll be able to point to the right direction for you to do revision so that you wouldn't waste a lot of time. So the exam questions and courseworks, they are not designed to trick you, but it should be a little bit challenging so that not everyone gets full marks. So everyone can make an effort. But anyway, I will try to go through those exam questions with you today. So basically, my part of teaching only covers actually 3 areas. The first area is channel modeling. Let's take a look at slides briefly. So yeah, my part of teaching actually only covers three areas. The first area is channel modeling. We need to model the physical existence of wireless channel before we can engineer the signal transmission. And then the second area is modulation. You have learned a lot from different modules in the past 3 years, I suppose, about Cis-Quam, about QPSK. So you know quite a bit about that area already. And then the third area is multiple antenna technologies, which is the area that your coursework is based on. So basically, we only have 3 areas for my part of teaching. So the exam paper this year will have 6 questions, where 2 questions come from 1 lecture, and you have to answer 4 questions out of 6, and you have to answer at least 1 question from each area, from each lecture. So do plan your time on answering questions, because, for example, if you look at one of the exam papers, so this is the exam paper for 2014 to 2015, and for example, the first exam question is in that year was about multiple access techniques. So do plan your time according to the marks. If you write an essay here, you wouldn't have time to do the things afterwards. So let's just dig in and go through these exam questions. I wouldn't write down all the answers to you, but hopefully I would be able to point you to the right direction. And if you have any questions when you go through these exam papers, please do send me an email. It's the same as how you do your coursework. If you send me an email, I will always reply you with some tips and the direction to go, but I wouldn't give you the exact answer. Okay. So the first question here is describe 4 multiple access techniques, and in each case, explain why the number of supported users is limited. So this is from slides page, sorry, not here. So this is from slides page 6. So the first one, page 6, the first one is support different users but differentiate them in the frequency domain. And the second one is TDMA, which is differentiate them in time domain. And then the third one is CDMA, which is to modulate different users onto different codes. And the third is SDMA, which is differentiate different users based on their locations. So can you tell me, for example, let's just directly go to the most challenging one. So for example, for SDMA, what is a resource that limited the number of users? So basically, different users, they are at different positions. And what is fading channel actually? You have a base station, for example, in the middle. And then different users, they are at different locations. They are of different distance to the base station. And they have different surrounding environments. So the fading channel here is unique to a user. But if a user is too close to another user, these two channels can hardly be differentiated. That's why different users, it will be hard to support too many users if they are all too close to each other in terms of angle, in terms of environment, in terms of position. And for CDMA, basically we have a limited number of signal codes to support different users without encountering interference. So that is CDMA. And then for TDMA and FDMA, obviously we have limited amount of frequency bandwidth and limited amount of time slots in order to support users without interference. So basically, there is always limitation in resources. We cannot support a limited number of users. Okay, that is the first question. And then the second question, it is a quite important one. It's about the decision theory. So this is so once again, I want to emphasize that for the equations in the slides, you are not required to memorize them. If they are memorize all the complicated equations, for example, you don't even need to memorize Gaussian PDF, for example. So in the exam papers for the exam questions, normally I would either ask you to expand on the equations that I offer here. For example, here I already offer Q function. You don't need to expand what Q function is. It's integral on Gaussian PDF. You don't need to expand it, but you do need to use it. Either something like this, or it would be I write down the equation there and then ask you what are all the parameters for, what are their meanings. So basically, you don't need to memorize very complicated equations, but you do need to know how to use them. And another example is you need to be able to derive equations for multiple alternate technologies, including space-time block code and multi-user detection. We will touch upon them a little bit later. So basically here it is about decision theory. So figure 1 is BPSK, figure 2 is QPSK. So figure 1 has 1 bit, figure 2 has 2 bits. So now I tell you here that you need to use Q function to derive the bit error ratio. So the first question is you need to derive the expressions for the bit error ratio of BPSK and QPSK. Your expressions should use Q function and should be in terms of EB over N0, where EB is the average phasor energy per bit, and N0 is the noise power in both real domain and imaginary domain. So this is a complex power for the noise. So this one is on page 71, I think. Okay, so it starts from here. Let's try to derive the equations. So basically, what you need to remember is that in the end, when you have Q function, here, the bit error ratio is a function of P, which is a distance, from the cancellation point to the decision boundary. This is P. And then this is sigma, which is a standard deviation of the noise power in one domain, either real part or imaginary part. So let's come back here. This QPSK, the first step is that you need to use Q function. So what is the BR for QPSK? So you have what is the distance from the cancellation point to the decision boundary? It is A here. And then the standard deviation is sigma. So this is a BR for BPSK. What is BR for QPSK? So now you have 2 bits, but it's symmetric. So the BR for both bits are the same. So for all the 4 cancellation points, their distance to their decision boundaries are all B. So BR is B divided by sigma. This is the first step. Second step, you need to decide what is the relationship between the E0, E, B, and also A here and B here. So E0 is the average power on the symbol. So for BPSK, you have two symbols, 2 cancellation points. Both are of power A square. So this is E0. And then for BPSK, you only transmit 1 bit. So the power consumed on symbol equals to the power consumed to each bit. So now you link A with E, B. For QPSK, we have 4 symbols, and each one is of power B square for the real part, and then B square for the imaginary part, and then takes average. We got E0. This is average power. And then we transmit 2 bits. So E0 equals 2 times EB here. So now we link EB to B. So we can put EB, we can link EB to B here. We can link A to A in Q function. And what is sigma? Is standard deviation of the noise power in real part or imaginary part. So N0 equals 2 sigma square. So now you link N0 to sigma. So it's only one step away from representing this as a function of EB over N0. I'm not going to write that down. So it's your job to finish that. So here, use your result. Otherwise, discuss how this BPSK and QPSK modulation schemes compare in terms of bandwidth efficiency, as well as in terms of immunity to noise and phase jitter and nonlinear distortion. So basically, bandwidth efficiency is about how many bits you transmit with given a bandwidth. So you need to argue, you need to compare their BR. So now the BR is in the form of A and B, but if you link them to EB over N0, then both BR are in the some form of EB over N0. Then you need to compare their BR to tell me in the answer that which BR is better, which one is worse, or they are equal. And then also explain that BPSK, for example, transmit 2 bits, and BPSK transmit 1 bit. So with given bandwidth, which one give you better bandwidth efficiency? So obviously the one that transmit 2 bits is give you better bandwidth efficiency. And then immunity to noise, phase jitter, and nonlinear distortion, they are determined by, from page 71, that determined by minimum Euclidean distance, which is A and B for BPSK and QPSK, and minimum phase rotation, which is which you can observe from the constellation diagram. I'm not going to say that here. And then peak to average power ratio. We're going to revisit all these 3 concepts from other exam questions. So I'm going to just leave it there for now. So the second question in that year was, first of all, when a mobile station is moving into a macro cell, and there is a base station positioned on the roof of a city building, describe the channel impairments that could be expected for the wireless communication between this mobile station and base station. I have actually emphasized quite a few times in the slides. So during the revision, it would be really helpful if you look at all these questions first, and then you go through the slides. So basically, the answer can be found in channel modeling, for example, for example here, page 13. So I have 3 levels of fading. The first level is path loss, which has something to do with distance, because signal power would decay over distance. And then the second level is shading effect, which has something to do with your environment, because buildings or vehicles, they could cause blockage between a mobile station and the base station. And then the third level is fast fading. It is caused by multipass. So you have a line of sight, you have a lot of non-line of sights. They arrive at a destination with different delay and Doppler and phase rotation. And sometimes it's together constructively, sometimes destructively. And also you have the fading channel for the fast fading. It would change in both frequency domain and time domain that cause frequency selectivity and time selectivity. So basically, it would be helpful if you answer these questions in bullet points and then elaborate them a little bit further. So basically, you need to answer how they are modeled. For example, for path laws, we have the free space path laws. We have shielding effect, which is log normal distribution. We have Hatta model, which is modeled by measurements, modeled by collecting data from measurements. So you need to explain a little bit how you model those fading channels, but also help me to find some marks for you. So if you write a really long essay, it would be really hard for me to find the points that you deserve. If you write them in bullet points, say first of all, you have the first level of the fading for path laws, and for path laws you have 3 models, which are free space path laws and ground reflection path laws, and also Hatta's model. Then it will be easier for me to find marks that you for you. Okay, the second question is consider adaptive transmit diversity scheme which conveys complex. So there's only one symbol, but you use n transmit antennas and then 1 receive antenna, I think. So yeah, 1 receive antenna. So you transmit 1, so you have n transmit antennas. They all transmit X, the same symbol. And then they all experience fading channel. So we ask you to draw a block diagram for the scheme and show how the transmitter can exploit the knowledge of H, which is a fading channel here. And also derive expression for the received signal Y and explain how this indicates the diversity order. So this is on page let me see. So basically, this is here on page 119, transmit diversity. So you transmit 1 symbol. So in the slides, there are M transmit antennas, and then you transmit them to the receiver. So as a transmitter, can anyone tell me what P are? What are they? So these are pilot symbols, which are used to estimate fading channel, so that as a transmitter, you have the knowledge of H1 of H1, H2, all the way to HM. And can anyone tell me what W? R, what are W's? So they aim to compensate for the effect of fading. They try to cancel the effect of fading from the transmitter. So basically you have everything here. This is the first equation and this is the second equation. And you use the knowledge of H as a transmitter so that the effect of fading is canceled. You only have power here because phase rotation would corrupt your constellation, but power can be compensated by power control. So from here, you can see that obviously the diversity order is M because you have M replicas of the fading channel's power. This is not very difficult, and this is all from the slides. Okay, so that's the exam paper for 2014 to 2015. That is the first exam paper we look at today. Let's look at the second one. Second one is, this one, 15 to, yeah, 15 to 16. Okay. Second exam paper. This is really important. These are all important questions. So the first question is about modulation. So we have a system quant. We have a system quant constellation, square system quant constellation draw field on here. And basically I tell you that the average power is this. You need to show, first of all, you need to show how do you get this average power. And then you need to derive the minimum Euclidean distance, the peak to average phase energy ratio, and the minimum phase rotation between any pair of constellation points. And also you need to compare them to a star quant, which is not drawn in here. Yeah, how square quant is compared to square quant in all these three areas. So basically what I'm looking for is, let me see, page 89, I think. So here, what I'm looking for is this table. So you should be able to derive, you should be able to calculate this table by yourself during the exams when I only offer you a constellation diagram. This is a constellation diagram for system quant. And the one on the exam paper is for square quant. I'm going to spend a little bit time to derive that table again together with you today. Alternatively, you can go back to, I think it was in lecture 6. So you can go back, you can check the recording for my lecture 6. The important thing is that given a piece of paper, you should be able to derive this. You should be able to derive this, obtain this table by yourself. So I'm going to spend a little bit of time to derive it again together with you today. Let's first of all take a look at the square quantum constellation. So the first step, how do we get the average power? So first of all, how many rings do I have for square quantum constellation system quantum? So I have emphasized quite a few times, so I have 3 rings. The inner ring has 4 constellation points, all have the same amplitude. And second ring has 8 constellation points, all have the same amplitude. And the third ring has 4 constellation points, all have the same amplitude. So first of all, we have 4 constellation points in the first ring, and their amplitude is a square for the real part, and then a square for the imaginary part. And then we have 8 constellation points in the second ring. They are all of 9 a square for the real part or the imaginary part, and a square for the imaginary part or the real part. And then we have 4 constellation points on the third ring, which are 9 a square for the real part, and then 9 a square for the imaginary part. And then you take average of them all, which is 16 divided by 16, you get E0. So that is the first step. The first step is to link E0 to the constellation power. And then the second part is the minimum Euclidean distance. What is the minimum Euclidean distance for square quantum? So basically it's 2a. So you have E0 as a function of a. Euclidean distance is 2a. So you can represent minimum distance as a function of E0. And then the third step is peak to average power ratio. So we know the average is 10a square. What is the peak? The peak is the power of the third ring, which is 9a square plus 9a square. So the peak to average power ratio would be this divided by 10a square. Okay. And then what is the minimum? What is the minimum phase rotation? It is this angle here. How do we calculate this? So if we look at half of this angle is this much, and we draw a line here, it is a triangle where this side is a, this side is 3a. So this angle is arctangent a divided by 3a. And then this minimum phase rotation is 2 times of this angle. So you have the minimum phase rotation. That is for square quantum. Let's look at star quantum again. So now star quantum is a little bit more complicated. Let's go through this step by step again. So first of all, the first step is we have the distance between constellation points on the same ring as D1, and the distance between constellation points across different rings as D2. So there is a trade-off between D1 and D2. If we enlarge D1, then the first ring would have to go large. Then D2 becomes smaller. If we enlarge D2, then the first ring will have to shrink. Then D1 becomes smaller. So the simplest way is to set D1 equals D2. And then the first ring's amplitude is A1. The second ring amplitude is A2. So we have A2 minus A1 equals D1 equals D2. So A2 minus A1 equals D2 equals D1. Okay, that's the first thing we need to get, which is a relationship between A1, A2, and D1, D2. So, the second thing is we need to represent A1 and A2 as a function of D. So A1 alone as a function of D, and A2 alone as a function of D. So how do we do that? We know that this triangle is an isosceles triangle, which means this side, this side, and this side, they are of equal amplitude. They are both of amplitude D. Because constellation points, they divide the space equally. So this angle is 45. If I draw a line here, what is the angle of this one? Sorry. What is the angle of this one? This angle would be 180 minus 45 divided by 2, which gives you 67.5. Why do we need it? Because this side is D, this side is A1, and this side is A1. Because this triangle link A1 along to D. So if we divide if we take this angle out, triangle out like this. So this is 45. And then we have this angle is 67.5 degree. And then if we draw a line here, which is orthogonal to this D, then I divide D to two parts. So each part is d by 2. So here, this is d by 2, and this is a1. It's quite difficult to write it on my computer. It would be easier to write everything on board. But anyway, now because we know the angle here is 67.5, we can link A1 to D. So cosine 67.5 degree, cosine would equal to D divided by A1. So now we link D to A1. And here we have, if we put A1 to this side, we can also link A2 to D. So in the end, we have both A1, where is it? Both A1 and A2 as a function of D. Okay, why do we need that? Because the average power is, we have 8 constellation points in the first ring. We have 8 constellation points in the second ring. So the average power is a function of A1 and A2. And now we can put D in here. We finally link E0 to D. So for the exam question, the first question is to link the distance, to express the distance as a function of E0. So we need to represent A1, A2 as a function of D first, and then E0 become a function of D. Okay. The phase rotation. So because the constellation is equal-spaced, I said before, so the minimum phase rotation between 2 constellation points is 45 degrees. And the third step is peak to average power ratio. So the peak is A2 square. Average is E0. If you express them both as function of D, then in the end, you arrive at peak to average power ratio here. So basically, you need to complete this table by yourself. Could you promise me that you'll practice this before the exams, so to make sure that you can obtain this table by yourself on a piece of paper? So now, compared to when we compare star quam and square quam, which is better in terms of phase rotation? So star quam is better. It is more robust to phase jitter. Which one is better for Euclidean distance? So square quam is better here in terms of robustness against noise. Which one is better for peak to average power ratio, which contribute to the power consumption, hardware power consumption at the power amplifier? So star quam is better, the lower the better for peak to average power ratio. So yeah, this exam question is repeated again in later exam papers, which means this is really important. So please make sure that you practice that table. And then the second question is about the decision, about the decision theory. So basically, when we transmit QPSK, quam symbol over AWGN channel, and then we receive a signal here. And now I provide you with a Q function. You don't need to expand the Q function, but you do need to use Q function. And you need to reconstruct 4 bits, B1, B2, B3, and B4. So first of all, you need to decide on the decision boundary so that you can detect these 4 symbols. And secondly, you need to derive the BR for each one of them. So basically, this is from page 89, I think. So basically, this is here. So in the slides, I didn't differentiate the BR for each bit. Now I'm going to go through that with you again, in line with this exam question. So, so basically, the first 2 bits are for real part. The last 2 bits are for imaginary parts. They are symmetric. So I'm just going to go through the first 2 bits for you today. So the first important thing is where the decision boundary is. So for the first bit, I1, we can see that the decision boundary is the y-axis. So for all the consolidation points that have positive real part, the first bit is detected as 0. For all the consolidation points that have negative real part, the first bit is detected as 1. So how do we calculate BR? So for the first bit, we have 8 consolidation points, which are of distance of A to the decision boundary. So we have this one, this one, this one, this one, and all of this, and all of this. They are of distance A to the decision boundary. Then the BR is Q, distance to decision boundary, divided by sigma. And we have 8 constellation points that are of distance to A to the decision boundary. And then similarly, we have 8 constellation points that are of distance 3A to the decision boundary. We add them together and then take average. We get the BR for the first bit. So for the second bit, it is decided by the scale. So the decision boundary is decision boundaries. We have 2 decision boundaries here. Divide the consolidation points based on their scale. So if the received signal scale is smaller than 2A here, then it would be decoded as bit 0 for the second bit. If the scale is larger than 2A for your received signal in comparison to the decision boundary, then the second bit would be decoded as 1. So this is I2. I2 here actually is a third bit labeled on the constellation point. So for this BR, how many constellation points are of distance A to the decision boundary? We have 16 of them. So all of them are of distance A to the decision boundary. Because there are two decision boundaries, we also have the case where this consolidation point is of distance 3a to the decision boundary. So how many consolidation points are there that are of distance 3a to the decision boundary? We have 8 consolidation points that are of distance 3a to the decision boundary. And then we also have a special case where, for example, if this consolidation point cross decision boundary twice, then the detection becomes correct. So if the consolidation point cross the decision boundary once, then you will you count it as a mistake. If it's 1, then it's mistakenly detected as 0. But if it crosses the decision boundary twice, then it would be detected correctly. So we need to manage that situation. That situation is the consolidation point that is of distance 5a to the decision boundary. So how many consolidation points are there that are of distance 5a to the decision boundary? You have 8 again. And then you need to take average of all of these situations. You get the BER for the second bit for the real part, which is I2. So real part and imaginary part, they are symmetric. I'm not going to go through imaginary part again for you, but you do need to do that by yourself. Okay. So that's this exam question. So which bit is more vulnerable to bit errors? So basically, what you are looking at is the distance to decision boundary. So for example, if you have more consolidation points that are let me see, that are too close to the decision boundary, then it would be more vulnerable. So obviously, the second bit has 16 scenarios where consolidation points are right next to the decision boundary. So the second bit would be more vulnerable. Second bit for the real part, and also second bit for the imaginary part. I'm going to have a break here. This is the first video. I'm going to upload the second video separately later.